A predictive model is finalized and deployed. It passes all historical holdout tests with a 90% accuracy rate. Then, in production, it fails. The paradox of applied machine learning is that a binary classifier can boast high historical accuracy on a testing set, yet break down when deployed to drive a live production risk system. Overconfident risk models operating without explicit boundaries for error were a direct contributor to the 2008 financial crisis. Delivering a point prediction, a single best guess number, without explicitly quantifying the surrounding margin of error, is mathematically incomplete. It provides the system with false confidence. High historical accuracy offers an illusion of safety. If a model does not explicitly quantify its uncertainty for future events, standard evaluation metrics become useless to the decision-makers relying on them in production. Junior data scientists routinely fall into two specific traps when attempting to quantify this uncertainty. First, they use confidence intervals to bound their forecasts, when they actually need to construct prediction intervals to capture future observations. Second, they conflate a model's binary hit rate with probabilistic calibration. They assume that because a model guesses the right category often, its stated percentage probabilities can be trusted. To build trustworthy risk systems, we have to mathematically decompose uncertainty into its root sources, measure whether our stated probabilities actually match reality, and enforce honesty in our models using proper scoring rules. Mastering these specific distinctions is a prerequisite for moving from academic data science into the deployment of professional, resilient models. A confidence interval serves a strict limited function. It only quantifies uncertainty regarding an estimated parameter, like a population mean. This chart shows how boundaries must shift when forecasting. To bracket a single future observation, you must use a prediction interval. It is inherently wider, accounting for parameter estimation uncertainty, plus the inherent randomness of generating a new data point. The formula calculates this range by taking the point prediction, x, and adding or subtracting a standard normal critical value, z, multiplied by the standard error of prediction. That standard error of prediction decomposes into epistemic and aleatoric uncertainty. Epistemic uncertainty is variance from limited data, or imperfect model knowledge. It is reducible and shrinks as you gather knowledge. Aleatoric uncertainty is the inherent randomness in the system itself. Think of it as baseline measurement noise. It is entirely irreducible. Applying a confidence interval where a prediction interval is required guarantees you will systematically underestimate risk, leaving decision-makers blind to actual worst-case scenarios. When a model underperforms, the immediate reflex in data science is to collect a larger training set. Adding more data exclusively shrinks the epistemic variance. Aleatoric uncertainty sets a hard mathematical floor on predictive accuracy. Because this noise is an inherent system property, infinite data will never cross this boundary. In a demand forecasting model, if the epistemic parameter standard deviation is 15 units and aleatoric residual noise is 30 units, we calculate total variance by squaring and adding them. The square root yields a total predictive standard deviation of roughly 33.5 units. While wilder than either individual sources, the irreducible 30 units of aleatoric noise dominates the final error. Failing to isolate these sources wastes engineering resources, as teams chase more data for a model already completely bounded by irreducible noise. The second major failure mode happens when stakeholders take the probability percentages generated by a binary classifier at face value. Trusting those percentages requires calibration. A probabilistic forecast is well calibrated only if its stated probabilities mathematically match observed long-run frequencies in reality. If a meteorologist issues 100 forecasts stating a 70% chance of rain, and it actually only rains on 55 of those days, the model is overconfident in that specific range. This chart is a reliability plot. It graphs the model's predicted probability on the x-axis against the actual observed frequency on the y-axis. The 45-degree diagonal line represents perfect calibration. Plotting our weather data point at a predicted 0.70 and an observed 0.55 places it visibly below the diagonal. Points falling below this line universally indicate overconfidence. A model displaying this pattern requires mathematical recalibration, typically through methods like plot scaling, before its outputs are safe to use. This is distinct from sharpness, which measures how concentrated or confident the forecasts are. Optimizing a model to be highly sharp before you have proven it is calibrated is actively dangerous. It simply makes the model confidently wrong. A model can classify binary outcomes correctly 90% of the time, while simultaneously outputting overconfident probabilities. Without a reliability plot, this flaw remains completely invisible. Standard evaluation metrics and loss functions often fail to correct this. They can inadvertently incentivize models to misreport true probabilities just to minimize generic error. The solution is a proper scoring rule. This objective function achieves its optimal score only when the model reports its true, honest probability distribution. The standard proper scoring rule for binary events is the Breyer score, shown here. The core of the equation measures the gap between the stated probability, p sub I, and the actual binary outcome, y sub I, which resolves to exactly 0 or 1. Applying this to our weather example, the stated 70 professional architectures bound reducible epistemic gaps and irreducible aleatoric noise using prediction intervals. They establish calibration to prove reliability before increasing sharpness. It validates that integrity by using proper scoring rules to eliminate the incentive to game forecasts. These mathematical standards safely guide high-stakes environments, from setting safety margins in reliability engineering to preventing cascading failures in financial risk systems. A professional data scientist provides both the prediction and the mathematical proof of exactly how much a stakeholder should trust it.